Hello everyone, and welcome back to my online teaching platform. In this video, we'll be looking at one of the interesting topics in math. And this topic is one of the concepts under calculus, which is differentiation. Under this topic, we shall learn how to determine a change in one quantity as a result of a change in the other quantity. So if you have a function, let us look at this one. If I have a function, suppose I have a function which is y is equal to 2x. This is a linear function, so you can determine the change in y, the change that will occur in y, if there has been an increase in x value. So suppose you have the first x value to be 1. So if x is equal to 1, y will be equal to 2 times 1, and that will give us a result of 2. What if your x has been increased by 1? So if x has been increased by 1, you need to also determine the change that has occurred in y. So if x, the original value of x is 1, and it has been increased by 1, the new value of x will be, y will be equal to 2, then you open bracket, 1 plus 1, because the x has been increased by 1, and that will give us 4. So that will give us 4. So to determine the change that has occurred in y, you just subtract the new value of y. Sorry, you subtract the initial value of y from the new value of y. So the change in y will be 4 minus 2. 4 minus 2. It means y has increased from 2 to what? 4. And the change that has occurred is 4 minus 2. So the difference between the two results becomes the change that has occurred in y when x increases from 1 to 2, or when x has been increased by 1. All right. Now let us look at this diagram. We'll be looking at function. Let us look at the x and y plane. All right. Now we have the graph of the function y is equal to f of x. So y is a function of x. Now we have a point here. So this particular point. So we have a point where this line, let's say here is P. So if here is P and here is Q. All right. So we have a point on the curve where the line PQ touches the curve. So whenever you have a straight line touching the curve at only one point, it means that line is called a tangent, or the name of that particular line is a tangent. So this is the name, tangent. So the line PQ is a tangent. Now, let us indicate the values of x on the x-axis. So the initial value of x, we don't know it, so we can use x to represent the value of x here. So the value of x here, I'm using x to represent it. So if the first value of x from the point where the tangent touches the curve is x, then it means we need to find the corresponding y value. So I have to trace it to my y-axis. So it means wherever I see x in the function, I'll plug in x. So the function is y is equal to f of x. So when you replace x with x, you are still going to get f of x. So the corresponding y value of x is f of x. Now, let us indicate the other x value, because we have a right angle triangle over here. We are trying to determine the gradient of this particular line. So we are trying to determine the gradient of line PQ using the right angle triangle. So I can now trace this one to the x-axis. So I'm tracing it to the x-axis. Now, the initial value of x is here, but we are now getting another value of x. So we assume that we have added some number to x. X has been increased by a certain value. So we don't know that value, so we represent the value with h. So from here up to this side, I'm going to use h to represent that small increment. So if I've added h to x, it means the new value of x will be x plus h. So we have to get the corresponding y value of that x plus h. So I'll trace it to the line. Look at it carefully. Then I'll now trace it to where the y-axis is. So because you are dealing with the tangent, anytime you are finding the corresponding y value, you have to trace from the x to, and the line should be parallel to the y-axis until it cut the tangent. Then you trace it to the y-axis. So to get the y-axis, it means we have to plug in the new x value. So it's going to be f of x plus h. F of x plus h. All right. Now, let us determine the slope. Let us now determine the slope from this diagram. So we are going to now determine the slope of PQ, line PQ. So we can, let me put R over here. So the slope of PQ, so the gradient of PQ, let me put it over here, line PQ will be equal to, that is QR, it's going to be QR divided by, then we have our RP over here. So we have our RP, all right. So it's going to be QR over RP, all right. So let us determine our QR. Our QR will be the change in the Y. So that will be our f of x plus h minus f of what? X. So it means the f of x plus h is your y2, and your f of x is your y1. So you were taught how to determine gradient as change in y, that is y2 minus y1 divided by x2 minus x1. So the same thing be done to the denominator, which is the x2 minus x1. So if f of x plus h is your y2, it means the corresponding x value should be your x2. So our x2 is x plus h, then minus our x1, which is x. So we are going to get here to be x. So we continue to simplify. So our gradient becomes our f of x plus h minus f of x, then everything divided by x plus h minus x. So you could say that this x will cancel this x, and you'll be left with, you're now going to get f of x plus h minus f of x, all divided by h, all divided by h. All right, so this is the gradient of the line. Now, we want to find the gradient of the line at point P. We don't just want to find the gradient of the tangent, but we want to find it at the point where it meets the curve. So you could see that it means you have to now shift from your right hand side. You have to now start removing the small increment that has been added. So it's that you have to now move towards the x value. That's the initial x value. So that is when we are supposed to apply the concept of limit. So this becomes a function. So we will take the limit of what we have gotten as the as the h, that is a small increment, approaches 0. So you could see that on the graph, if x becomes the value that we are going to use, it means there will be no small increment. So for you to get back to where the P is, where the x value is the original x value and the y value is our f of x, it means what you have gotten, you have to take the limit of what you have gotten as the small increment that you have added is now approaching 0, meaning you are removing what you have added earlier. You are now taking it back. So you could say that the graph or your line PR will now move. All of them will move close to the point P, and there will be no H, or there will be no small increment again. So for you to determine the gradient at exactly point P, you have to take the limit of this particular function as the small increment approaches zero, meaning we are getting back to where the x is, and that is where the point is also located. So to get, so the gradient, so now we are finding the gradient of the same tangent, but now we want to get it at a particular point. That is the point where it cut the graph. So it's going to be gradient of the tangent at P. Gradient of the tangent at P will be equal to the limit of what you have gotten. So the limit of f of x plus h minus f of x divided by h, which is the small increment. As the small increment approaches zero, meaning when it becomes zero, it means you have now gotten back to where the x is, and that is where the P is also located. So now, when in calculus, when you have a limit of changing an output over a small change, the small change that has occurred in the input, as the input approaches zero, it is the same as dy. We use dy dx to represent it. So this becomes, so it means we are going to rewrite the whole thing as dy dx is equal to the limit of f of x plus h minus f of x, all divided by h, as the small increment approaches zero. So this is the formula that we'll be using to find the gradient of a tangent to a curve at a particular point. And this is the same formula that we use to find the gradient of any given function at a particular point. So anytime you want to find a gradient, you have to find the difference between the output, that is the new value that you have obtained when the input has increased, minus the original value of the output, that's the function itself, over the small change that has occurred. Then you take limit of everything as the small change approaches zero. So we shall look at how best we can apply this formula in finding the gradient of linear function, quadratic, cubic functions at a given point. But when you take your linear function, that one, the moment you differentiate or you use the formula that we have on the screen, you are going to get the gradient without considering any point, because it is already a straight line. But when it comes to the curve, you need to find a gradient at a particular point. So that is where you have to know the point that you are dealing with, so that after your derivative, you can substitute that value into the function to get the exact gradient at the given point. Thank you.